So let's revisit the idea of equivalence relations, and let's prove the following. So I want you to prove that the relation R defined on Z by x relates to y if x plus 3y is even is an equivalence relation. So you need to show that this relation is reflexive, symmetric, and transitive. Now the first thing you want to do is you want to start by understanding the relation. You need to make sure you know how the relation works. So maybe start by writing down some of the elements that are related to each other. So for example, if I take 5 is related to 7 because if I take 5 plus 3 times 7, that's 26, and 26 is even. But if I look at 8 and 9, this is 8 plus 3 times 9, that's 35. And that's not even. So 8 is not related to 9. Now if I look at 4 and 4, we're hoping that this is an equivalence relation, so 4 should be related to 4. So if I look at 4 plus 3 times 4, this is 16, and 16 is even. So 4 is related to 4. Okay, so we've kind of processed this relation a bit, and now we understand it a little bit better. So now let's start with our proof. So the first thing is we need to prove that the relation is reflexive. So this is the first part. We're going to show that R is reflexive. So let's start with our outline of our proof. So let's start with our outline. I'm going to take an arbitrary element out of Z, call it A, and then I need to show that A plus, right, I'm trying to show that so here's my start of my proof. Here's my end. I'm trying to show that A is related to A. What does it mean for A to be related to A? It means that A plus 3A is even. Well, A plus 3A is 4A. To be even, you need to be able to write it as 2 times an integer. It's 2 times 2A, where 2A is in Z. So we've outlined it. Let's write the proof now. Let A be in Z. Now we're going to consider A plus 3A. Then we can write A plus 3A, that's 4A. So A plus 3A equals 2 times 2A. So since 2A is in Z, A plus 3A is even. So that means that A is related to A. And we've established that R is reflexive. So that completes the proof that R is reflexive. Now let's prove R is symmetric. So again, we're going to start with our outline. We're going to assume that A is related to B. That's the start, and then the end of our proof. So the end of our proof will be that B is related to A. I'm probably going to need a little bit more room here. What does it mean for B to be related to A? It means B plus 3A is even, which means B plus 3A equals 2 times M for some M and Z. If I work forward now, I know that A is related to B, so this tells me that A plus 3B is even. So A plus 3B is equal to 2 times K for some K and Z. So if I solve for A here, I will get that A equals 2K minus 3B. And now if I plug this in to B plus 3A, this will give me B plus 6K minus 9B. And I kind of made myself run out of room here. So let me shift some stuff down. And then B plus 3A equals 2 times M for some M and Z. Well, now that I bought myself a little bit of room here, I get that this is 6K minus 8B. So this is 2 times 3K minus 4B. So this whole thing here is what I'm going to call M. Right here. So now that I have my outline, let's write up my proof here for symmetric. So proof, we're going to assume A is related to B, then A plus 3B is even. Therefore, A plus 3B equals 2 times K for some K and Z. And then what did we do after that? If we look at our outline, we solved for A. Solving for A, we get A equals 2K minus 3B. And then we're going to plug that in. Now, B plus 3A equals b plus 3, 2k minus 3b. This is equal to b plus 6k minus 9b. And we said that that was 6k minus 8b. And we factored out a 2. This is 2 times 3k minus 4b. So we're going to call that m. Let m equal 3k minus 4b, which is an integer. Now, what do we have? We have b plus 3a equals 2 times m. So b plus 3a is divisible by 2. Therefore, b is related to a. So we've proven that the relation is symmetric. So the last thing we need to do is we need to prove that R is transitive. So again, start with an outline of our proof. The start, you're going to assume A is related to B and B is related to C, and you need to show in the end that A is related to C. So you need to show that A plus 3C is even. So A plus 3C equals 2 times M for some M and Z. If A is related to B, then I know that A plus 3B is even. I also know, because B is related to C, that B plus 3C is even. So if A plus 3B is even, A plus 3B equals 2 times K for some integer K, and since B plus 3C is even, it's 2 times N. This is for some integers K and N and Z. And then what I'm going to do is I'm going to add my two equations that I have here together. So if I add on the left-hand side, you're going to get A plus 3B plus B plus 3C equals 2K plus 2N. Now look at what you're trying to get to. You want an equation that only has A and 3C on the left-hand side. So if I add, I'm going to combine these 3B and B to be 4B. And then I'm going to move this 4B to the other side so that I'm left with A plus 3C. It's 2K plus 2N minus 4B. So I can now write A plus 3C as 2 times K plus N minus 2B. And this is what I'll call M, this integer M that I was looking for. So now we've got the outline of the proof together. So let's go ahead and write the proof. And again, you're going to reference your outline as you go along. You assume A is related to B and B is related to C, and A plus 3B is even, and B plus 3C is even. Therefore, A plus 3B is equal to 2 times K and b plus 3c is equal to 2 times n for some integers k and n, adding these equations together, we get a plus 3b plus b plus 3c equals 2k plus 2n. Now, a plus 4b plus 3c equals 2k plus 2n, and a plus 3c equals 2k plus 2n minus 4b. And then remember, we factored out a 2. And you're going to say let m be equal to this integer k plus n minus 2b. Then we have a plus 3c equals 2 times m, and a plus 3c is divisible by 2. Therefore, a is related to c, and R is transitive. So we've established that R is reflexive, symmetric, and transitive, therefore it's an equivalence relation.